All right, so it's time for a little friendly competition. In general, the two paths compete and the one paths compete. And how do you know if you should do substitution or elimination, or whether you should follow the two paths or the one paths? You have a few things to consider. The structure of the substrate, methyl, primary, secondary, tertiary, allylic, benzylic, aryl, vinyl, all that stuff. The base, is it strong? Is it weak? Is it a good nucleophile or not? Is it in high concentration or not? There's a lot to consider. The solvent, is it protic? Is it aprotic? I don't really know. And temperature, we've not really discussed prior to now, but we'll get there. So first and foremost, the very top thing to consider is the substrate, the type of substrate you have. If you have an uncrowded substrate, like primary and methyl, that's generally going to make you lean toward a two-path. But can a methyl alkyl halide undergo E2? No. There's only an alpha carbon. There is no beta. So in fact, this primary methyl substrate generally does SN2, but E2 is possible if you're not methyl. This says beware of neopentyl. What is neopentyl? That's this. There's an alpha carbon, a beta carbon. Oh, there's no beta hydrogen, so you can't do elimination. And that beta is so crowded that it's hard to do even substitution, SN2 right there. SN2 is your only option. E2 is not even an option. But it's kind of crowded to even want to do SN2. Okay. E2 is terribly bulky base. Our favorite bulky base is Katbu. The book talks about a couple of others, DBU and DBN. You should maybe look those up, see what those are. What if you have a secondary substrate? Well, you can do the two paths. You can also do the one paths. You can do lots of things if you have a secondary substrate. If you look back through the majority of the examples we've talked about, tons of them were secondary. Yeah. If it's tertiary, what can you not do? SN2 is not allowed when it's tertiary because it's too crowded. So you can do E2 because you're not reacting at the alpha carbon in elimination, you're reacting at the beta carbon. So E2 is possible, and if you have a strong base, you're going to do that. If you don't have a strong base, you're going to do the one paths. The one paths often come together in alkyl halides. SN1 is generally the favored path, but anytime you make a carbocation, because these lead to carbocations, right? Anytime you have carbocations, all hell breaks loose. You can do substitution or elimination. You can do both. Substitution will generally be the favored product. Okay. All right, we said the base / the nucleophile. I should really write that there also. If you have a strong base, you're going to do elimination. Almost exclusively elimination via E2. Because that strong base is very good at plucking a hydrogen, not as great at attacking a carbon, not as great at being a nucleophile if you have bulky things. If you have not bulky things, you can do SN2, but you have to consider steric stuff as well. Strong bases, who are the strong bases? Well, you have this acid-base chart memorized in your little brains, and we go from strong base toward weak base in that chart. And we're going to draw an arbitrary line that says hydroxide is the weakest base that we will refer to as strong. Hydroxide is the weakest base that we will refer to as strong. In that acid-base flow chart that's on our page that you have in your brain, hydroxide is the weakest base that we will consider strong. There's a lot more that are stronger than hydroxide. Hydroxide is the weakest that we'll consider strong. Did I say that enough times? Okay. So that's if you have a strong base. What if you have a weak base? We're going to make a carbocation if we have a weak base. Carbocations mean the one paths. That means SN1, E1. What about the solvent? If it's aprotic, that generally favors the two paths, but really SN2 is the fastest overall in an aprotic solvent, but E2 can be pretty quick in it as well. Protic solvents favor carbocations. That means the one paths again. High temperature favors elimination. What? We haven't said that before now, but if we had, let's say, some sort of thing that we add a nucleophile to, we end up with that nucleophile substituting and getting bromide as a side product. Okay, cool. If we add some sort of thing and it's the same nucleophile, except this time I'm going to call it a base, that base can react with a hydrogen like this. I guess I should draw arrows up there. That base can react with a hydrogen, give you that, plus Br minus, plus base with an H, and maybe a positive if it didn't have a charge originally. Okay. Thermodynamics. Oh boy. Thermodynamics says delta G is dependent on delta H and delta S. Delta G is dependent on delta H and delta S. Delta S, remember, is entropy. And so when you have more entropy in the products than you do in the reactants, that reaction is generally favorable. Well, 3 products have more entropy than 2 products. So this top half was a substitution reaction, and the bottom one was an elimination reaction. Entropy favors elimination. So when you increase the temperature, that's got to do with delta H, I know. When you increase the temperature, it gives you more elimination products because it also pushes toward a more negative delta G. We can really get into more thermo talk if you want to, but what you need to know is high temperature increases the percent elimination. High temperature favors elimination over substitution. The end. All right. So are we ready to put all this information together in the all too imperfect? Note, this chart is not perfect. It's a good guide to get you started, but there are still places where the chart is not perfect. It falls down. It's not perfect. Have I warned you enough? All right. We said the substrate is the very first thing to consider. So you start out by asking yourself, what kind of substrate do I have? Do I have a methyl substrate? Do I have a primary substrate? Do I have a secondary substrate? Or a tertiary substrate? Note, we are not putting allylic and benzylic on this chart because things get crazy when you include those. We'll talk about it. Remind me. Methyl. There's 1 carbon. Can't do alpha beta stuff. So there's only one reaction possible because we don't have methyl carbocations. That is not a thing. We get SN2 and SN2 only when you have a methyl substrate. That's kind of nice. The rest of these are not quite as nice. When it's primary, that's not crowded. SN2 is generally what's favored, but E2 possible with a strong base. And who do we consider strong base is? Hydroxide and to the left. Yeah. Okay. We said secondary, everything is possible, so I'm gonna skip that for a minute. We're gonna go over here to tertiary. Tertiary SN2 was not possible. We said E2, SN1, and E1 were all possible. How do you decide between those? You ask a second question. Do I have a strong base? If the answer is yes, you do E2. If the answer is no, you make carbocations. That means SN1, E1. It's getting real crowded down there. SN1, E1. SN1, E1 makes a carbocation. The favorable path is SN1 unless you turn up the temperature, then you can get E1 to be favored. Yeah? All right, since since secondary can do multiple things, I'm going to need to clear up some space so that I have secondary more room for it. All right, so under secondary, since everything is possible, we need to narrow the field a bit. The first question to ask is, do I have anions in my solution? Having anions likely leads you away from a carbocation. Yeah? Having anions, if the answer is yes, you're probably going to go down a 2-path. If the answer is no, you're going to make carbocations and do SN1, E1. And the favored path is generally SN1, but if you turn up the temperature, you can get some E1. Yeah? If the answer is yes, you have to ask another question. Are the anions that I have strong bases? Is it a strong base? We're going to go real crooked up here and say no, yes. Told you I needed more room. If yes, you have a strong base, you're going to do E2. If no, you don't have a strong base, you're going to do SN2. Yeah? So really, if you're methyl primary or secondary with anions that are a weak base, you do SN2. If you are primary with a strong base, secondary with a strong base, you do E2. I should have kept going. If you're primary with a strong base, secondary with a strong base, tertiary with a strong base, you do E2. E2, yeah, strong base, kind of a requirement. If you are secondary with no anions or tertiary with no anions or a weak base, you're going to do carbocations, SN1, E1. That's what all that chart says, yeah? Does that chart talk about solvent? No, because we can sort ourselves into a bin, meaning a bin like this. We can sort our reaction into a bin without considering solvent. Solvent is really only a consideration if you're comparing two reactions. Reaction A versus reaction B, which reaction happens faster? Well, maybe you have to look to solvent in that case. But otherwise, solvent is low on the list. And also remember that temperature kind of flip-flops what's favored. Substitution versus elimination. Yeah. One more thing, I mentioned it in the beginning of this. Is allylic on this list? No. All of these things, SN1, SN2, E1, E2, they could all happen with allylic alkyl halides. Is benzylic on this list? No. But all of these things can happen with benzylic alkyl halides. So you have to think for yourself a bit more than this chart allows when you have something that's allylic or benzylic. Vinyl and aryl are not on this list, but vinyl and aryl don't really do SN1, SN2, E1, E2. So that's kind of okay. You ready to see if we know how to use this chart? Let's do it. All right, in this first one, I have a primary alkyl halide. Under primary, it says SN2 as the major thing. SN2, when you have hydroxide is the weakest of the strong bases. So hydroxide could do E2, but it's a very small, weak strong base. Yeah, you heard me. It's a very small, weak strong base. So it's generally going to do SN2 substitution. Can you turn up the temperature and get E2 elimination? Yeah, but let's draw a little SN2 mechanism. Like that. We get this as our product. It's an alcohol. But I thought SN2 reactions are favorable in aprotic solvents. It's true, but this is a protic solvent. But did we consider the solvent to help us choose? Nope, we didn't. That's our product. Done. Okay. Next, we have a tertiary alkyl halide. All right, the next question to ask, do I have anions? Do I have a strong base? No. Therefore, SN1/E1, and the major product is going to be SN1. But this is an aprotic solvent. I don't care. My chart says solvent shouldn't be considered unless you can't really decide otherwise. So, mechanism in blue. Diva leaves and leaves behind a carbocation. Carbocation gets attacked by water, like so. Water cleans up, and we get this. This is the product of SN1. This carbocation, can it shift? No. But this carbocation can undergo E1 elimination. Pluck a hydrogen from the beta carbon, dump in electrons toward the carbocation, alkene, E1. The major product is substitution. Yeah? Alrighty. And the last one, we have a tertiary alkyl halide. Anions, strong base? Yes. Therefore, E2 is what we should do down here as the only reaction to do. E2. So I got an alpha and a beta. All my betas are the same. I don't have to consider Zaitsev anti-Zaitsev. I should have said that for the E1 above as well. All my betas are the same. So my strong base plucks a hydrogen, from the beta carbon. That's a funky wonky arrow. Dumps in electrons to make a pi bond, kicks out the bromine, and we get this thing. E2. Whoop whoop. It's the only product. Check it out. The middle reaction made this alkene product. The bottom reaction made this alkene product. They make the same product, but how they got there is very different. And unfortunately for you, that's important to an organic chemist. Knowing which mechanism it goes through is very important to us and temporarily important to you so that you can do well. We made the same product. We got there different ways. It matters to us. All right. That was so fun. How about some more? I think you should pause and analyze these on your own and see if you can figure out what mechanistic path we should go through, and go ahead and try to draw the mechanism and or the products yourself. This is me pausing to encourage you to pause. Well, here we go. We've got a secondary alkyl halide. Anions present? Yes. Are those anions strong base? No. Therefore, SN2. I'm going to keep analyzing. We have a secondary alkyl halide. Oh, look, all these alkyl halides are the same. Anions present? Yes. Strong base? Yes. E2. Secondary alkyl halide. Anions present? No. Therefore, SN1, E1. Secondary alkyl halide. Anions? Yes. Strong base? Yes. Therefore, E2. Alright, let's go off to the races with some mechanism drawing. The first one is SN2. That means iodide attacks the backside of that carbon, does an inversion of configuration to give me that product. Done. SN2 is fabulously short mechanism. Alright, E2. Gotta label our alphas and the betas. Zaitsev says take the hydrogen from the beta with the fewest hydrogens. That will give you your most substituted alkene, which is usually the major product. So in blue, I have done that. That makes this my major product, probably. But before I go off and say that, let's draw some purple. If I take that purple hydrogen over there, without drawing the mechanism of taking that purple hydrogen, because it's generally not good practice to draw a whole bunch of arrows on the same reactant, I make this purple product. Yeah, definitely the blue is the major. Okay. All right. Next. SN1E1, that means Diva leaves and leaves behind a carbocation. That carbocation can be attacked by HOET. That HOET gets the positive charge and another HOET cleans up. This product that I'm drawing is the product of SN1. It came through a carbocation. Ooh, I need a squiggle right there because that needs stereochemistry. Okay. That carbocation, I'm going to have to go down below. We'll have to erase in a minute. That carbocation can also undergo elimination, E1. So we're going to take the hydrogen from down there, fold in electrons like so, and give me this alkene. Okay. That carbocation can undergo an anti-Zaitsev elimination as well. Oh, my. Anti-Zaitsev elimination to give me this alkene. Alrighty. So we've got this carbocation that led to these 3 products. But anytime you have a carbocation, you have to watch out for rearrangements. I should have written down here, this is an E1 Zaitsev, and this is an E1 anti-Zaitsev. Let me flush some stuff off the whiteboard, and I'll be right back. All right, so this blue carbocation can undergo a shifty shift, a rearrangement, a hydride shift to get me a brand new purple carbocation. And that purple carbocation can undergo SN1 and E1 as well. Yep, I'm serious, unfortunately. So we need an ethanol, a little HOET, to attack that carbocation. And we make this product. And then you got to clean up, it's not water. Clean up, everybody clean up. We get this purple product. Oh, we're going to have to stick it over there, because that's all we got room for. Is that an asymmetric carbon? Do I need any dashes, any wedges, any squiggles? Nah, it's good as is. That's my SN1. That's my only SN1 from my purple carbocation. But I could also do E1 with my purple carbocation. Yeah. I've got alpha, I got beta, I got beta, I got beta. 3 different beta hydrogens, but 2 different types of beta hydrogens. Those 2 terminals are the same. This beta, if I eliminate from this beta, I actually make this product again. So I don't need to draw a second way that the same product is made. There is a second way that the same product is made, but I'm worried about making new and different products. So I'm going to take my ethanol and pluck a hydrogen there, and amidst all this chaos, this is my E1 anti-Zaitsev. Let's do a little summary. We've got our purple carbocation, and that purple carbocation led to this SN1 product and this E1 product, and would also lead to a second E1 product, but it's the same one as down here. Yeah? I had to erase all the other information about all the other reactions because this SN1E1 took up the entire slide. Yeah, SN1E1 involves carbocations, and while that's great and convenient because we love carbocations because we got familiar with them previously, they sometimes can make a lot of products. SN2 and E2 don't do that. That's kind of great. Yeah. All right. Back to where we were. Example number 4. Example number 4 said E2 is what we should do according to our flow chart. E2 is what we should do, but wait. There's something that I remember being a little bit different, a little bit unique about Katbu. Do you remember? There are 2 different beta hydrogens. Beta on the left is Zaitsev beta. Beta on the right is anti-Zaitsev beta. We have said Katbu is so bulky that he cannot squeeze himself to even pluck that little hydrogen out of that little armpit kind of spot right there. This little hydrogen is in a little armpit. Katbu is too big to squeeze himself in there and pluck that armpit hydrogen. So he's got to pluck this hydrogen and this hydrogen only to make that product. Yep. Well, let me redraw all the products so I can make a summary statement. What's really nice about this slide is that it shows how the same reactant, I'm just separating those, the same reactant, all the same reactant, under different conditions does different things. So last unit, it was all about alkenes, add this new reagent, add this new reagent, add this new reagent, and it did different mechanisms based on the reagent. It's similar this time, but we've got the same substrate in all of these, but the conditions are slightly different for each one of them, and we get different products for each one of them because of that. And actually, we already did say that this guy is the major for my second reaction, and we did not say among all the SN1E1 stuff who's major. That would be this guy, because he's the substitution product that came from the most stable carbocation. Yeah? It's a good summary, this slide. I like it. You like it? Maybe not. Okay. All right. But wait, there's more. I've got a secondary alkyl halide. Anions? Yes. Strong base? No. Cyanide is a CN minus. It is not considered a strong base. It's a rare kind of thing. A lot of students want to make that a strong base, but cyanide is not considered a strong base. His pKa is like 9.1. His conjugate acid pKa is like 9.1. Hydroxide 15.7. So yeah, he's weaker than that. So we're going to do SN2. Attack that carbon from the back side. We would get inversion of configuration, but this carbocation, this is not a carbocation, not at all. Scratch that. This carbon, this asymmetric carbon, is not defined with a dash or a wedge, so I cannot define a dash or a wedge over here. I need to know that it's SN2 and would be inverted, but when it's not defined, I need not define it in the product. Yeah? One other little thing about this guy, look, he made a new carbon-carbon bond. Remember, that's kind of what organic chemists love a whole lot, the Holy Grail? Yeah, cyanide can do SN2, make a little carbon-carbon bond. All right. We've got a primary alkyl halide, and our flowchart says, SN2. Almost exclusively SN2 when you have a primary alkyl halide. Why do I have these two things over here? What are those there for? Well, when I have hydroxide in solution with a carboxylic acid, acid-base reactions happen faster than other things. So we're first going to do an acid-base between those two because the kinetics of an acid-base is so fast, you cannot hope to do a substitution or an addition or an elimination before an acid-base takes place. So acid-base happens first. This thing is actually my anion, my nucleophile that's going to do my SN2, like that. I really get this product. I almost made that a benzene. That is not a benzene. Yep, this product. 3 carbons got attached to my oxygen. It's an ester. Ta-da! All right, in the next one, I have a primary alkyl halide that says SN2, almost exclusively. This is a strong base, but I have an acidic hydrogen. So that sodium hydride is not there to be my nucleophile. That sodium hydride is there to pluck a hydrogen off of my alcohol to give me an O-. That O- is then my nucleophile that will attack and do my SN2 of my Br. The reason this undergoes an intramolecular reaction like that is because when I fold that up like so, it makes a reasonable sized ring. So intramolecular is favored to make a ring when you make a reasonable sized ring. Wait, what? What is considered a reasonable sized ring? A 3-membered ring is reasonable. We've made epoxides, remember? A 4-membered ring, not super reasonable. A 5-membered ring, a 6-membered ring, very reasonable. So how do you know if you should make a ring or not? This compound I should point out, is a bifunctional compound. It has two functional groups in it. It's a bifunctional compound. In order to do a cyclization like this, you need a bifunctional compound. So when you have something bifunctional, it's often you'll need to adjust one of the functional groups, like deprotonate this alcohol, and then it will do its own intramolecular thing. There's a whole section in the textbook about whether you should do inter or intramolecular. Probably worth a little bit of time to look at it. Everyone's favorite. It's time for synthesis. I wish I would go back and change those two things to not say from an alkane, but to say alkyl halide on both of them. Because alkanes are the next functional group that we're going to learn about. We can't make these things from alkanes yet, but coming soon to a theater near you, we will be able to make them from alkanes. All right, so in this top one, I'm trying to make what functional group? An alkene. An alkene is going to require an elimination reaction. The good news is, with my adjustment right here, I do know how to make an alkene from an alkyl halide. It's going to be an elimination. But is it going to be E1 or E2? It all depends on what reagents I choose. So if I want to make this from an alkyl halide, the halogen definitely needs to be on this carbon or that carbon to make it most easy, right? Hopefully you see that. But the deal is, it's not different. It's the same whether I put the halogen here or there. It's just a cyclohexane. So there's my halogen. How do I do an elimination to get from one thing to the other? What reagent do I need to add? Well, if I add a strong base, it's going to do elimination via E2. If I add a weak base, it might do elimination via E1. Did you hear I changed my words? I said might. If I add a weak base, it's a secondary alkyl halide. So if I add a weak base, as in something that's not anions, that would actually lead me to SN1 and E1. So I'm going to avoid that path altogether. I'm going to go down the route of my flowchart, down the route that leads me to E2 and E2 only. So in order to make a secondary alkyl halide do E2 and E2 only, I need an anionic strong base. So from there, the possibilities are pretty wide. I can do Naomi. She's an anionic strong base. Katbu is an anionic strong base. Lots of things, lots and lots of things could be added here and get that product. If I want to hedge my bets, I could heat this thing a little bit because heat favors elimination. So I could heat this thing with Naomi, heat this thing with Katbu, and yeah, it's probably going to give me that product. If I really wanted to add a weak base, I could add Homie, but I definitely need to heat it a lot in order to get elimination, the E1 path to be favored. So Homie's not the best choice, but if you are going to choose him, he's got to be cooked a lot. All right. Next. I'm also trying to make an alkene in the next one. And if I'm trying to make that alkene from an alkyl halide, I erased my words, but from an alkyl halide, makes sense to me to put the alkyl halide here. But could I also put the alkyl halide out there? Wow, that's really crooked. Could I also put the alkyl halide out there? I could potentially do either of these. Let's see how that relates to my flowchart. In this top example, I've got a tertiary alkyl halide. I'm wanting this tertiary alkyl halide to do elimination. Tertiary alkyl halide leads to SN1E1 if I have a weak base, but if I have a strong base, it's going to do E2. I'm going to lean toward the strong base route. So then the question is, alpha, beta, beta, beta. Uh-oh. I want anti-Zaitsev elimination. That means I need to add a large bulky base. Kotbu is one of our favorites. Let's heat it just to hedge our bets. But Kotbu is one of our favorites. We could also use DBU. It's a bulky base. It does elimination. E2, anti-Zaitsev. And that's what we want. E2, elimination, anti-Zaitsev. Yeah, yeah. What about down here? Down here, this is a primary alkyl halide. Primary says SN2. Uh-oh, we don't want SN2. We want E2. It says under my flowchart, E2 is possible if a strong bulky base or a strong base. So I could do something like Naomi and really cook it here to try to guarantee that I'm getting that elimination product. That's my best bet probably in this bottom one. If I add too bulky of a base, it's really hard to squeeze in there and get that little hydrogen in the armpit. But yeah, Kotbu could potentially do this bottom one too. Yeah, we see how this is working? All right, we got more. If I am trying to make this next one, it says from an alkene. Yes, I realize I'm drawing it in a different orientation. I know. I look back through my knowledge, through my reactions that we've done, and I say, I remember making an oxygen-carbon bond in several of the reactions that we've done. So let's imagine breaking that oxygen-carbon bond right there, and imagine that this thing could be made from this and this, sort of, kind of, but I'm not finished yet. In order to bring those two things together, it works best if that guy is charged, and this one is going to need a leaving group, needs a leaving group. So those two things definitely react together to get me that thing up there. But it's not generally allowed to start with something that's charged, so we'll have to go back to the neutral carboxylic acid, like this one. And this says we have to start with an alkene. This is an alkyl halide. It is not an alkene. But I know how to make alkyl halides from alkenes. I know how to make that alkyl halide from this alkene. So reagents. What reagents need to be added? From here to there, I need to deprotonate. How about hydroxide? Hydroxide will definitely deprotonate a carboxylic acid like that. From here to there, oh, I got to revisit old knowledge. Oh boy. Alkenes, that's addition reactions. Alkenes, I need an anti-Markovnikov alkyl halide. The only way I know to make an anti-Markovnikov alkyl halide, boron stuff, followed by Br2 and Naomi. That makes me an anti-Markovnikov alkyl halide. And then all you got to do is add those two things together. That says add. Wow. All you got to do is add those two things together, and that will come up with that ester up top. That one's a bit longer than the last one. There's one more on the slide. Let's do it. If I want to make this thing, how do I do that? So the first thing to check is this has 5 carbons. The thing I'm allowed to start with has 5 carbons, so I don't need to make any carbon-carbon bonds. That's good. Phew. All right. I remember that ketones, that's what this is, right? I remember that ketones can tautomerize. So if I think backwards a little bit, that ketone could have been this thing, this enol that tautomerized to make that ketone, or it could have been this enol that tautomerized to that ketone. Is there a right one and a wrong one? Well, because of what I'm told to start with, I do think one is much easier, much more clear than the other. So this has my functional group on the terminal end, and my blue one has the functional group on the terminal end. My green one is internal, that's probably not going to be as easy. So forget the green one. Let's work with the blue. So if I work with the blue, enols, I remember, were made from alkynes. So that 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, okay. Sorry. Whoops. That alkyne has to be on the terminal end in order to make this enol on the terminal end. So this alkyne will make that enol, yeah, and then that will tautomerize this. Okay. All right. If we continue on the backwards train here, because I have to start with an alkene, not an alkyne. This is where I start thinking forward a little bit instead of backwards. And I don't know, it's hard to tell students the best way to approach a synthesis problem. It is. It's really hard. Practice is going to be the only thing that's helpful. But, yeah, this is where I start thinking forward a little bit. I mix together my forward and backward thinking. Here's what I start thinking. If I'm allowed to start with this alkene, I'm going to need to add some halogens to it in order to eliminate those halogens and turn it into 2 pi bonds. Right now I've got 1 pi bond. I need to get to 2 pi bonds. The only way to get to 2 pi bonds is to eliminate 2 halogens. So that means I need to add 2 halogens to this alkene. The only way that I know of to add 2 halogens is something like Br2 addition to that alkene. That's going to give me 2 Brs added on neighboring carbons like that. All right. Then I need to eliminate to get to this alkyne. I have a primary and a secondary alkyl halide. If I'm going to try to do E2 here, I'm going to need a strong base, maybe even high temperature, a strong base that will doubly eliminate that stuff. This is one of the common strong bases that are used to doubly eliminate. Is it mandatory that that's the conjugate, that's the strong base that you use? No. That strong base is just a common one when you're trying to doubly eliminate. All right. That will give me this terminal alkyne, and then from here to there, that's an addition reaction. It's Markovnikov. I need acid, mercury. I officially need mercury because it's a terminal alkyne, and water. Acid and water would kind of be okay if you just gave me that, but I officially need mercury because it's a terminal alkyne. And then nothing is needed reagent-wise from the enol to the ketone. It's an automatic tautomerization. So you don't even have to write this at all. I think it helps students a lot to take this ketone and draw the enol from which it came, because I think that helps their thought patterns, their process. You do not have to draw that enol, but you do really need to draw kind of the rest of the stuff that I have drawn. All right. So this is a long one. It's a hard one. Imagine if we also had to make carbon-carbon bonds at the same time. Yeah? Can you imagine? Yeah. Those old reactions intermingle with new reactions, intermingled with old reactions, to put together some pretty sophisticated syntheses for this unit. All those reactions from old can be combined with all these reactions from new to do a lot of stuff. You now know reactions in the 3 major categories: substitutions, eliminations, and additions. Yeah. We can make a whole lot of stuff with those 3 categories. I think that's good enough. Goodbye.